Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about an example where we have data from a normal process with mean mu and variance sigma squared. In this case, both parameters will be unknown. And what we're going to be using as prior will be independent non-informative priors for mu and sigma squared. Okay, let's begin. So that's the example I would like to talk about with you in this video. This is the one that we're going to be working on together. So as you can see, right, the random variable of interest is the number of miles a car can be driven between charges with a given set of batteries. Okay. What we're assuming about that random variable is that it is normally distributed with mean mu and variance sigma squared. If you recall, what we did before is we assumed that we had enough knowledge about this process so that the variance sigma squared could be regarded as known. Okay? In this case, we no longer assume that. So both mu and sigma squared will be unknown parameters. And as you know, in Bayesian statistics, parameters are considered as random variables, so we're going to need to treat them as such, so they have a distribution, and we're going to need to impose or come up with prior distributions for these two parameters. Okay. So the other ingredient besides our priors will be the likelihood. That's the other important ingredient in Bayesian statistics, right? So in this case, we have data. We have 10 observations, and this guy here, S sub x, represents the sample standard deviation from that sample of size 10, and the sample mean is 135 in this case, sample standard deviation 20, and as I said, the sample size that we have is 10, right? Now, about our prior. As advertised at the beginning of the video, what we're going to be using as our prior is what we used in another video, right? Now we have two parameters of interest, so we would need a joint probability distribution for these parameters, but we are going to be assuming independent priors, independent non-informative or Jeffreys priors for mu and phi, and phi is just, you know, a little bit of a change of variables that we're doing here, or that we used before to derive the posterior. Remember that it was just a small change, a notational change. Okay, so anyway, so since we are considering that the priors are independent, the prior that we are going to be using for mu would be proportional to the constant 1, and the non-informative prior for phi, or in other words for sigma squared, will be just the reciprocal of phi. Okay, so 1 times this guy, we end up only with the reciprocal of phi. Okay, that's Jeffrey's prior. Okay, so that's the prior that we're going to be using, and we would like to answer 2 questions. One, we would like to find the posterior probability that mu, the average number of miles that can be driven using these batteries. That set of batteries is less than 130 miles. And the second question that we would like to answer is to come up with a central 95 posterior credible interval for mu. Okay, so here we go. So solution. So first, our sample size is 10, right? The sample standard deviation sample standard deviation happens to be 20, and the sample mean x bar (135). Okay, so let me remind you that we're going to be using reference prior, non-informative prior, that is proportional to the reciprocal of phi. Okay? Okay, so first problem. We want to find the posterior probability that mu is less than 130. Okay? So let me write it down like this. Instead of the posterior probability that mu is less than 130, let me write it down like this. Probability that mu is less than 130 miles given our sample, right? So let me first write it down in let me write it down like this. x1 comma x2 up to x10, right? We have a sample of size 10. That's what we want. Okay, so let me remind you something that we learned when we derived in detail the posterior distribution of mu given a sample size of given a sample of size n, right, under these conditions, that these observations come from a normal process and both parameters mu and sigma squared are unknown. Okay, so let me just remind you, we know that, and let me write it down like this, that the posterior probability of mu given a sample of size n is proportional to the posterior probability in terms of a transformation, right, that we denoted by t, right, given that same sample, and what we know is that the posterior distribution of t given our sample looks like this. The expression was 1 plus t squared divided by n minus 1 to the power, what we had here was a fraction, right, minus n minus 1 plus 1, oh sorry, plus 1 divided by 2. Okay, so when we see that expression is the kernel of a t distribution with n minus 1 degrees of freedom, right? So in our particular case, this particular example, what we're going to have is that the posterior probability of mu, given our sample of size 10, will be proportional to something that looks like this, but you know, we're going to make a few changes accordingly. So here n, the sample size, was 10, so we're going to have a beautiful line, right? Same goes for this guy here, right? So bottom line, what we have is a t distribution with 9 degrees of freedom. Okay? And remember that we derived in detail that posterior distribution. Okay? Okay. So that's really important for what we have to do next. Okay? So remember that the first question that we want to answer is we want to find the posterior probability that the average number of miles that can be driven on a set of these batteries is less than 130 miles. Okay? So let me rewrite that problem, right? So what we want is something like this, right? So now let me go from this, right? Having here explicitly that this is the posterior, I mean, given that we have observed a sample of size 10, let me just drop that. Okay? Okay. So, next step. If you recall, right, we had to go from mu to t. We had to do this transformation because at first, when we first obtained an expression for the posterior distribution of mu given the sample, right, it had an expression, it had a kernel that we couldn't recognize, right? So we transformed mu, right? We came up with this transformation to come up with another variable t. That transformation that goes from mu to t was a linear transformation, and this one we were able to recognize. Okay? Okay. So just like we have normal random variables with some mean and some variance, different from 0, different from 1, and then to turn that normal with some mean and some variance into a normal 0, 1, you have a formula, right? It's a similar process what we have here. This guy here is a standard t distribution, and that transformation that we used was similar to those c-scores, right, that we know from courses in introductory statistics. Okay, so let me remind you what that transformation looks like in our case, right? How we went from mu to t. And again, we're basically going from a non-standard t distribution to a standard t distribution. Okay, so recall that t, right, our transformation looked something like this. It was mu minus x bar divided by s sub x, where that guy represents the sample standard deviation of our variable x, and then divided by the square root of n. Okay, remember that was the transformation, right? That's what we used to go from mu to t. Okay, so now the thing is, this is the this guy here is the probability that we want, the probability that mu is less than or equal to 13. But right, when we transform, then we get to use a standard t. So we have tables for standard t distributions, and in the case of R, right, that pt and qt has to do with standard t distribution. Okay, so then if we do that, if we transform mu doing this, then we get to use those functions or those tables if we're doing this by hand. Okay, makes sense? So here we go. Let's do the transformation. Let's use that transformation here. So we're going to write an event that is equivalent to this, mu less than 130, by the way. So what we have to do is we subtract the mean, the sample mean, x bar. Oh, sorry, not what I wanted to do. So we subtract x bar, we divide by sx divided by the square root of n. We do the very same thing on the right hand side of that inequality. In this case, let me do it with numbers. 135, we know, right, that the sample standard deviation was 20. Okay, so we have a 20 here. And we have a square root of 10. Okay, now let me change this. I want this to look a little better. That looks better. Okay, so we're just again using that transformation to go from a non-standard t to a standard t. Okay, let's keep going. So now this guy on the left hand side becomes a t, right? Less than something. We have to do the math. Let's do the math using R. So let me launch R. And what we need is 130 minus 135 divided by 20 divided by the square root of 10. There we are. So let me round that to 4 decimal places. That should be enough. Okay, so the event that we had in mind at first, the probability that our parameter mu was less than 130 miles, is equivalent to just having the probability that at t with how many degrees of freedom, right? So since we have a sample size of 10, this guy here is a t distribution with 9 degrees of freedom, right? So that event that we wanted at first, the probability that mu is less than 130 miles, is equivalent to the probability that a t distribution with 9 degrees of freedom is less than negative 0.79, roughly. Okay? So, let's find that probability. We know that there's a function that we can use, a built-in function in R that we can use to evaluate the CDF at a particular point, right? So that function happens to be PT. So what we need is the point at which the CDF will be evaluated. So it's negative 0.7906. The other argument that we need is the degrees of freedom, in this case 9. So that's the probability that we want. Okay? So the probability that the average number of miles driven using a set of batteries like the ones we have in this problem, well, the probability that the average number of miles driven using this set of batteries is less than 130 miles is roughly 22%. Okay? Okay. So that's part A. Let's talk about part B. For part B, what we want to do is construct a central 95% posterior credible interval. Why we say central? Because, for instance, we could evaluate the CDF up to a point where we have 95% probability, right? But that is not exactly what we want. What we want is something like this. So we're being very, very specific, right? So what we want is to have something like this. So we know that this transformation that we have here has a central t distribution with 9 degrees of freedom. Okay? So we want two numbers from a t distribution with 9 degrees of freedom such that the area between them is 1 minus alpha, right? If we're talking about, in general, about the 1 minus alpha credible interval, what we want is to use critical values, numbers coming from a t distribution, such that the area to the left of this guy, and if we're talking about t distribution with n minus 1 degrees of freedom, right, such that the area to the left of this guy is alpha divided by 2. Oops. Alpha divided by 2, right? And then, since we know that t distributions are symmetric, we want to have this guy, the positive version of this guy, here, right? And then we are going to satisfy, well, those guys are going to help us satisfy this, that the area or the probability between them is 1 minus alpha, right? Okay, so in other courses we have used that trick. All we have to do next is just solve for the parameter of interest, right? So in this case we just have to solve for mu. So solving for mu, let me just copy paste this guy. What we're going to end up with, right, is we have to multiply on both sides by this guy. This guy is positive, so the inequalities won't change directions, but then what we have to do is add, right, x bar on both sides, and then we're done, right? Okay, so we multiply by this guy, we add an x bar, and that's it. What we have there now is just mu, and that's the parameter of interest. So this guy, right, well, these two guys form a central 1 minus alpha credible interval for mu. Okay, so this is 1 minus alpha times 100% credible interval. Oops, what did I do wrong here? Oh, never mind. Credible interval for mu. Okay, there we are. Okay, so now let's find the 95% credible interval that we want in this case. 95% credible interval for mu. So let me find the lower credible limit. That's what I'm going to be calling this guy in our particular case. Okay, so it would be just x bar, which is going to be 135, times I'm going to need a critical value, right? So I'm going to be using R to find that critical value, coming from a t-distribution with 9 degrees of freedom, such that the area to its left is 0.025, right? So here we go. So now, instead of using that function pt, which helps us evaluate the CDF of at a particular point, what we're going to be using is the function qt, that is going to help us find a quantile that has an area of 0.025 to its left for a t-distribution with degrees of freedom equal to 9, right? Okay, so that's our guy. Let's round that guy to 4 decimal places. That should be enough. So that's my critical value times, and now what we need is the sample standard deviation 20 divided by the square root of n. So this is what we have, 20 divided by the square root of 10. Great. So let's use R to find that guy, right? And there's no need for this negative here. That is already built in here, so let's have it that way. Okay, so let's find it. So it would be 135 and then plus this guy has a negative here. That's the critical value, so that negative sign is built in there, times 20 divided by the square root of 10. Okay, so that would be the lower credible limit, or LCL for short. Let's find the upper credible limit. So this is our guy. Now we want the positive version of this guy. We know that t-distributions are symmetric, so this guy better be just the positive version of what we had here, right? Okay, just for fun, let's double check. So what we would have here, right, is 0.975, right? So that means that the area that we have to the right of that quantile is 0.025, or 2.5% to its right. Okay, so as predicted, the difference between the critical value that we had for the lower credible limit, right, is just the all we have to do is this guy is the positive version of the one we had before. Okay, so now let's just modify this guy, right? So it's going to be 975, right? Okay, so 149.30 roughly. So the 95% credible interval for mu is between 120.7 miles and 149.3 miles, right? Roughly. Okay, and that's it. Okay, well, let's summarize what we did. So what we wanted to do is we wanted to analyze data coming from a normal process with mean mu and variance sigma squared. Both of these parameters are now unknown. So what we did is we had to place a prior distribution for both of them. The joint prior is the product of two independent prior distributions, one for mu, one for phi. Phi represents sigma squared, right? And we used reference priors for these guys. For mu, something that is proportional to 1, and for phi, or sigma squared, we used 1 over sigma squared, or which is the same 1 over sigma squared. Okay, and then using what we did before, remember that under these conditions we derived the posterior distribution of mu given the data, right? So what we showed back then, was that the posterior distribution of mu given the sample was a t-distribution with n-1 degrees of freedom. So we just used that. But something else that was useful from that derivation was the relationship that there was between mu and t, right? So what we said is that that transformation that takes you from mu to t is similar to the c-score that you use to turn any normal into a normal 0, 1. So we're going from a non-standard t to a standard t, and then we get to use a table for a standard normal, or functions like the ones we used here, qt and pt. Okay, so using those we were able to find the posterior probability that we wanted and the critical values to construct, in this case, a 95% central credible interval for our parameter of interest mu. Okay, well, that's it. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.